Okay, so welcome back to another video. So in today's video we have another improper integral, the integral from 0 to infinity of the error function square divided by x squared dx. Our error function is our argument in terms of x. So the error function is defined as the following formula. So let's see, error function of x is equal to 2 divided by the square root of pi multiplied by the integral from 0 to x of e to the negative t squared dt. Okay, and so this function is heavily used in a lot of probability and partial differential equations, PDE, and this kind of helps define based on using the Gaussian integral, which I've used several times in this in past videos, but actually this time we're actually going to use Gaussian integral again another time for this, so just keep a mental note. And we're also going to be using this error function a lot to help calculate this improper integral itself, so just be aware of that and just give you a heads up. But any of all that stuff out of the way, I already defined the definition of the error function, so let's actually evaluate this. I'm going to define this our given improper integral, so I'll just denote this as capital I is equal to the integral from 0 to infinity of the error function square and then divided by x squared dx. Okay, and now I think what we want to do, I think you guys probably can say the same too, is we'd like to integrate this by using integration by parts. So we know the formula u times v minus the integral of v times du, so we need to choose what we want to integrate and what we want to differentiate, our two functions. So I think the easiest function to pick to integrate is our 1 over x squared. So if that's the case, that means we have to differentiate the error function, so the error function squared of x. But how do we find its derivative? Well, let's actually figure that out. So let's see, so d over dx, that's in terms of dx, it's in terms of x since our input is in x. So let's see, the derivative of the error function square of x. Okay, so how about I replace the error function square of x, and then I'll put this out here. So the way to integrate this error function square of x, how about I like to treat this as the error function x as its argument and then square as a quantity and then square. So this means I can actually use our chain rule. So meaning this is 2 times the error function of x. So the degree cancels by 1, so we're just down with just 1 degree. But then we have to multiply with our derivative of the inputs. So the derivative multiplied by the derivative of the error function. And instead, I'll replace that with what we define as our formula. So it's the derivative of 2 divided by the square root of pi divided by, or multiplied by the integral from 0 to x of e to the negative t squared dt. But this is actually not that hard to show because you could actually use the fundamental theorem of calculus. So this means that we just, the derivatives and the integrals cancel each other out. So this means the only thing left is that we just have to plug x in for t. So therefore we get that this is just 2 times the error function of x and then multiplied by 2 divided by the square root of pi and then multiplied by e to the negative x squared. And also using fundamental theorem of calculus because you have to differentiate this bound here, but since the derivative of that's just 1, so it's good on its own. So therefore I'll clean this up. So we get that this is 4 times the error function of x multiplied by e to the negative x squared divided by the square root of pi. So with that, now we can actually do the actual integration by parts. So how about I write this in orange? So let's see. What I said was we're going to differentiate our error function and we're going to integrate our 1 over x squared. So this means I'll let u equals the error function square of x. Then that means du is equal to this one over here. So 4 times the error function of x multiplied by e to the negative x squared divided by the square root of pi dx. And so therefore dv is equal to 1 divided by x squared dx, and that v, when we integrate this, is just negative 1 divided by x. Okay, so we have that. Now we just have to use our integration by parts formula just to plug in our pieces together. So therefore, u times v minus the integral of v times du. So it means this is, let's see, so we have that this is negative the error function square of x divided by x, and that's evaluated at our bounds from 0 to infinity, and then subtract that with v times du. Let's see, there's a negative here, so I'll just factor out that negative outside, so it's a plus, and then our integral from 0 to infinity of the same thing over here, so but it's just x is in the denominator with the 2. 4 times the error function of x, e to the negative x squared, and then divided by square root of pi x dx. Okay, let's focus on evaluating this piece over here. So the negative error function square of x divided by x from 0 to infinity. So let's just plug in our terms. So this means this is negative error function square at infinity divided by infinity, okay, and then minus, so negative error square of 0 divided by 0. Okay, and there's one thing to note is that the and you can calculate this yourself, but the error function evaluated at infinity is actually just equal to 1. So if you square that, you're still going to get 1. So that'll just replace that. So thus, we can say that this is 1. Let's see, this is square, so yeah, negative 1 divided by infinity. But we know that that actually is just going to approach 0. So this will just be 0 over here. And then a plus, so then I just factor out the negative out here. The error function of 0 squared divided by 0, that's actually going to be a 0 over 0 indeterminate form. So therefore, we're actually going to have to be using L'Hopital's rule to evaluate this. So let's see, I'll write this as in terms of limits. So the limit as x approaches infinity of the error function square of x divided by x, which we see that this is 0 over 0. This is a indeterminate form. So over here, L'Hopital's rule. Okay. So that means we have to take the derivative of the numerator and the derivative of the denominator. So let's see, I'll just keep going. So this is 0 over here, and then plus limit as x approaches 0. So the derivative of the error function square of x, which we said that this was over here, and then derivative of x is just 1. So really we're just left with just the numerator itself. So if x divided by, or e to the multiplied by e to the negative x squared, and then divided by the square root of pi. Okay, but then we plug that in. We're gonna get that we plug x. This is going to be 0, and then we plug this. This is 1. So that means this whole thing is going to equal 0. Okay, so that means over here it's just 0. So now all that's left we need to calculate is just this little integral over here. And now I'm going to calculate this integral just by writing this in orange. Okay, let me write so far what we have. So far capital I is equal to, and I'll factor out a right over here. I'll factor out the constants, but instead I'll factor out a 2 and a square root of pi outside of that. So we get that this is 2 divided by the square root of pi, then multiply by the integral from 0 to infinity of 2 times the error function of x, e to the negative x squared, and then divided by x dx. Okay, now let's actually change this up a bit. So how about I define I as a function in terms of t. So this means when I rewrite this, well, not really rewriting, it's just well, it is in a sense rewriting it. So I call this the function I in I of t. So it means that's equal to 2 times the square, divided by square root of pi, then our integral. And then this time, this is going to be 2 times the error function of t times x, and then e to the negative x square, and then divided by x dx. Okay. Let me just underline this in black so we know what we're have to deal with right now. So now let's actually use Feynman's trick and actually differentiate this function. So this means when I differentiate this in respect to t, so that means I prime of t is equal to, let's see, so constants just remain the same, well, because we're only dealing with in respect to t. So let's see, I have the same thing. Okay, but before we continue writing on the rest, let's actually figure out how to integrate our error function of t times x. Okay, so let me write this over. Let's see, d and then dt of erf tx t times x. Okay, so therefore I can write that as d times dt of 2 times the square root of pi, multiply the integral from 0, and then the argument is tx, so I'll put a tx as the top bound, and then e to the negative t square dt. So then this means that when I integrate this, or when I differentiate this integral, that means we can just use fundamental theorem of calculus. So let's see, so we get that this is 2 times the square root of pi. So I plug t times x into this input over here, but we get that is t squared x squared, but we need to integrate, or we need to differentiate this bound, so we get that this is just x, then multiply by e, and then negative x squared t squared. So that's the differentiation here. So when I substitute this back in, notice that the x's from both the numerator and the denominator cancel. And actually, I can actually factor out a 2 over square root of pi. So let me fix that. So this means we get that this is 4, and then divided by square root of pi times square root of pi, and the square roots cancel out, so it's just pi. And then the integral from 0 to infinity. Let's see, I set the x cancel, and we're just left with still just 2 times e to the negative x squared t squared dx. Okay, and then I can actually just rewrite this our exponent parameter a bit. So I can actually just factor out negative x squared. So this is, let's see, 4, then pi, integral 0 infinity of 2 times e to the negative x squared, and then just multiply that with 1, and then plus t squared, and then dx. Okay, cool. So now we just need to figure out how to integrate this. So now what we can do to integrate this is I'm going to do a u-substitution. So coming from over here, let me actually rewrite what we're dealing with. So we have 4, then pi, integral 0 infinity of 2 times e to the negative x squared multiplied by 1, and then plus t squared dt. Okay, and now, like I said, we're going to do a u-substitution. So let's do it this way. All right, let me integrate this in black. So we're going to let u equals x times the square root of 1 plus t squared. Okay, then that means du is equal to just, and we're integrating this in respect to x. That should be an x over here. Then integrate this in respect to x. This is just the square root of 1 plus t squared dx. And I'll just divide, I'll divide the square root of 1 plus t squared to both sides, so that I get just du, and then divided by square root of 1 plus t squared, which is equal to dx. And so therefore I can actually do the rest as a substitution. So this means we have 4 pi, And then, okay, no, now we gotta plug in our new bound. So x is equal to 0, that's still 0. And then infinity, that's still infinity. Let's see, dx, so this means we have, this is just e to the negative u square, and then divided by the square root of 1 plus t square, and then dt, or du. 1 over the square root of 1 plus t square, it's still a constant because it doesn't depend on u, so I'll just factor that out outside. So I get that this is, let's see, 4, then pi times the square root of 1 plus t square. Then we have our integral from 0 to infinity of e to the power u, e to the negative u squared du. And also because got that, I can also factor out the 2 outside, so that means the numerator from the outside will also become 8. So let's see, this is going to be 8 over here, and then this is going to be 8 over here. Okay, but in case you haven't noticed, this is actually the Gaussian integral over the half line, since we're integrating this from 0 to infinity instead of the whole extension of the real line. So if you want to know how to evaluate the Gaussian integral, I'll just leave that video in the description below if you want to check that out yourself. Plenty of resources out there too. But because we're integrating this over the half line, note that the Gaussian integral integrated over the extended real line is equal to square root of pi, but it's half, so we just divide that by 2. So therefore, this is just 8 divided by pi. I'm just rewriting what we have from earlier, plus t squared. Okay, then multiplied by the square root of pi divided by 2. So therefore, we just clean this up. Square root of pi divided by pi. So we just use our rules of exponents. So that means it's just pi to the power negative 1/2. So that's the square root of pi into the denominator, and then you divide by 2, so it's 4. So it's 4 divided by the square root of pi multiplied by the square root of 1 plus t squared. So going back, we established that I prime of t is equal to over here. So 4 divided by square root of pi, and then square root of 1 plus t squared. All right, cool. Okay, so now, but we want to evaluate this in just I, since we said that I is equal to our original given function. So this means we're just gonna have to take the indefinite integral both sides. So integrate both sides in respect to t equal 4, then square root of pi, then multiplied by 1 plus t squared dt. Okay, and so I can actually just factor out a, obviously we know that this is just I of t, and then over here this is 4 square root of pi, and multiplied by the indefinite integral of 1 divided by the square root of 1 plus t squared, then dt. Now, we're gonna have, now to actually integrate this, we're actually gonna have to do some u-substitution. Okay, so this time when we're doing a u-substitution, but instead I'll use in terms of t. So this means I'm gonna let t equals tangent theta. Then that means when we differentiate both sides, that means this is dt equals secant squared theta d theta. All right. Okay, and now with now that we have the pieces we want, so this means I'll plug in back. So this means we have let's see, dt is just secant square theta, and then 1 plus tangent squared theta. That's actually equal to secant squared theta. That's just one of the trig identities, but take the square root of that, we're gonna get just secant theta d theta, and then they cancel, so that means we're just left with secant theta in the as our indefinite integral, and we just have to integrate that. So to integrate this, let's actually expand this a little further. How about I'm actually going to multiply and divide a tangent theta plus secant theta. So over here, that means secant theta, then multiply that with tangent theta plus secant theta, and so I said divide. So tangent theta plus secant theta d theta. Okay, so let's do the u substitution from here. So u equals tangent theta plus secant theta. Then that means du is just equal to secant squared theta plus tangent theta secant theta. Then we just plug the pieces. So let's see. Yeah, because this will cancel, because if you just distribute, you get secant theta times tangent theta, which is this, and then secant times secant squared. So that means the numerators cancel. So we're just left with just 1, and then divided by what we have set for u. So it's 1 over u du. And so that's not difficult to show the integral. So this is just the natural log of u, where we plug, so u is equal to tangent theta plus secant theta, and then plus c. But let's rewrite this a little bit so we get this in terms of t. So then we have the natural log of, we're just strictly dealing with positives, so I'm just writing parentheses in this. So let's see, tangent theta is just t, and then plus secant theta, where that's actually equal to the square root of 1 plus t squared, and then plus c. Okay, so therefore, now I take this integral, replace this with here. So we get that, so far we get that I of t is equal to 4 times the natural log of t plus the square root of 1 plus t squared, then divided by the square root of pi plus c. Okay, so now of course we have to actually find what our constant c is equal to in order to, before we continue further. But we can actually, but this is not that hard to show. We can actually just use the most basic case. We'll just let t equal 0. So if I plug t is equal to 0, then that means, let's see, I of 0. So we go back to over here. If we plug 0, so this means this is 2 divided by square root of pi, then the integral from 0 to infinity of, let's see, so this is 2 times the error function of 0 times x, that's just 0, then multiplied by e to the negative x squared, divided by x, and dx. But clearly, the error function of 0 is actually just going to equal 0, so that means this whole thing's equal to 0. Okay? So that means going back to here, so we've shown that I of 0 is equal to 0, so we have our little initial condition, not initial condition, but we found the condition we want to solve for our constant c. So now if I plug 0 back into our formula over here, so this means I of 0 is just equal to, let's see, so it's 4 times the natural log of 0 plus the square root of 1 plus 0 squared divided by the square root of pi plus c, which this means if I plug 0 for everything in here, that means, let's see, 0 plus 1 plus 0 squared, that's just 1, so it's 1. Ln of 1 is just 0, the whole thing becomes 0. So we're just left with c, but we've shown that using the initial condition, it has to equal 0. So our standard I of t is just equal to just the same thing, but c is equal to 0. So for ln of t plus the square root of 1 plus t squared divided by the square root of pi. Okay, like so. Now, the last thing we need to do is, since we're given that we want to show that I is equal to our given integral over here, but we expanded this in terms of our parameter t. Notice that if I were to plug t is equal to 1, that means, let's see, so this is just 2 times the error function of 1, or just x, error function of x, then everything here, then it's going to be the same thing as this here, which we've derived earlier, that's coming from our original integral that we're given. So this means that's what we wanted to show. So if I were to plug I1, then we get that this is 4 ln of 1 plus the square root of 1 plus 1 squared divided by the square root of pi, where that's actually just equal to 4 times the natural log of 1 plus the square root of 2 divided by the square root of pi. And there you have it. we have come to our little conclusion. So this means 3 dots. The integral from 0 to infinity of the error function square of x divided by x squared dx is simply just 4 times ln of 1 plus the square root of 2 divided by the square root of pi. And there we have it. Not too bad if you ask me, under this orange box over here. Now, that's actually pretty cool if you ask me.